Our home in the vastness of space is a galaxy known as the Milky Way. It is a vast, swirling collection of stars, gas, and dust, a cosmic city we are a part of. The name itself comes from the ancient Greeks, who saw the faint, glowing band of light across the night sky and described it as a river of milk. Other cultures have seen it differently. In China, it is the Silver River, and in the Kalahari Desert, it is the backbone of night. This galaxy is our island universe, and we are on a gentle journey within it. The Milky Way is a specific type of galaxy called a barred spiral. This means it has a bright, elongated bar of stars passing through its very center, and from the ends of this bar, majestic spiral arms unfurl and wind outwards, much like a pinwheel. These arms are regions of greater density, filled with bright stars, gas, and dust. We do not see this grand spiral structure from Earth because we are located inside it, looking out from within one of the arms. Our galaxy is ancient, having been formed around 13.6 billion years ago, making it nearly as old as the universe itself. It is one of the original structures to form after the dawn of time, a stable and enduring home that has been evolving peacefully for billions of years. The scale of our galaxy is difficult to comprehend, but it is deeply calming to consider. The main disk of the Milky Way is approximately 100,000 light-years across. A single light-year is the distance light travels in 1 year, which is an immense journey. To cross our own galaxy from one edge to the other, a beam of light would need to travel for 100,000 years. And yet, this vast structure is also incredibly thin. While it is so wide, the galactic disk is only about 1,000 light-years thick. This makes its proportion similar to a thin vinyl record or a flat plate, a delicate structure spinning gracefully in the cosmos. We are located in a quiet, comfortable part of this galactic disk. Our solar system resides within a smaller, partial arm known as the Orion Arm, or sometimes the Orion Spur. It is a more peaceful region, tucked away between two of the larger, more massive spiral arms, the Sagittarius and Perseus arms. Our position is fortunate, as it is not in the dense, chaotic center, nor in the sparse, empty outer regions, but in a stable and calm galactic neighborhood. Our sun is located about 27,000 light-years away from the galactic center. This means we are in the galactic suburbs, far from the intense activity at the core. This distance allows us to have a clear and beautiful view of the galaxy's structure, the bright band of the Milky Way stretching across our night sky, which is the combined light of billions of stars from the denser arms and the central bulge. Just as the Earth orbits the Sun, our entire solar system is on its own grand orbit around the center of the Milky Way. This journey is incredibly long and slow. It takes our sun approximately 230 to 250 million years to complete one single lap around the galaxy. This vast span of time is known as a galactic year, or a cosmic year. The last time our solar system was in this position, dinosaurs were just beginning to roam the Earth. The galaxy turns with a slow, steady, and predictable grace. The Milky Way is populated by an immense number of stars. Current estimates suggest there are between 100 billion and 400 billion stars within our galaxy alone. Each one is a distant sun, many of which are likely to have their own families of planets. This vast stellar population creates the gentle, collective glow of our galaxy. It is a city of stars, and ours is just one of many. When you look up at the night sky, even on the clearest night far from city lights, the vast majority of these stars are invisible to your naked eye. Of the billions of stars in our galaxy, we can only see a few thousand, around 2,500 at any given time. These are just our closest and brightest neighbors. The rest are so far away that their light blends together into a single soft glow, forming the hazy band of the Milky Way. This beautiful band of light that we see, the Milky Way itself, is our unique perspective from inside the galaxy. We are looking edge-on through the galactic disk, like being inside a flat pancake and looking toward its center and edges. The light we see, is the combined overlapping glow of billions of stars, gas, and dust clouds located in the denser parts of the galaxy, particularly in the central bulge and the surrounding spiral arms. The galaxy's center is a region of great density, packed with stars. At the very heart of the Milky Way lies a supermassive black hole named Sagittarius A star. While this may sound dramatic, our galaxy's central black hole is relatively peaceful. It is not actively and violently consuming large amounts of material, but is mostly in a quiet state, a sleeping giant at the center of our spinning stellar city. Its gravitational pull is what calmly holds the central stars in orbit, anchoring the galaxy's core. We cannot see this galactic center with our normal eyes or telescopes that detect visible light. The entire region is hidden from our view by thick, intervening clouds of interstellar gas and dust. These clouds act like a veil, absorbing and scattering visible light. However, astronomers can peer through this veil using other types of light, such as infrared, radio waves, and X-rays, which can pass through the dust and reveal the densely packed stars and the quiet center of our galaxy. The part of our galaxy that we can see, the stars, gas, and dust, only makes up about 10% of the galaxy's total mass. The other 90% is a mysterious, invisible substance known as dark matter. This dark matter does not shine, reflect, or absorb light, so we cannot see it directly. We only know it is there because of its immense gravitational pull, which holds the entire galaxy together. It forms a vast spherical halo that surrounds the visible disk, and its gravity is what keeps our galaxy from flying apart as it spins. The 10% of visible matter, known as luminous matter, is what forms all the beautiful things we can see. This includes all the stars, the glowing nebulae, and the swirling clouds of gas and dust. This is the material that is gathered together to form our sun, our planet, and even our bodies. Our galaxy's disk is not perfectly flat. It has a slight, gentle warp in it, meaning the edges are bent, somewhat like a vinyl record that has been left in the sun. One side of the disk appears to be bent up, while the opposite side is bent down. This is a common feature in spiral galaxies and is part of its natural structure. This gentle warp in our galaxy's disk is thought to be caused by the gravitational influence of our nearest neighbors. The Milky Way has several smaller companion galaxies, and the two largest of these, the Large and Small Magellanic Clouds, are in orbit around us. Their gravity pulls on the edges of our galaxy's disk, creating a slow, rippling tug of war that has bent the disk out of shape over billions of years. Our Milky Way is not alone in space. It is part of a small community of galaxies known as the Local Group. This group is a collection of over 50 galaxies, bound together by gravity. Most of these are small, dwarf galaxies, but the Local Group is dominated by two large spirals, our Milky Way and the Andromeda Galaxy. This group is our extended galactic family, all moving together through the universe. The Andromeda Galaxy is our closest large galactic neighbor. It is a massive spiral galaxy, slightly larger than our own, and it is located about 2.5 million light-years away. This distance, while vast, is close enough on a cosmic scale that Andromeda is the most distant object you can see with the naked eye, appearing as a faint, fuzzy smudge of light in the night sky. Like the Milky Way, Andromeda is also a beautiful spiral galaxy. It also has a barred center and tightly wound arms, and it is surrounded by its own system of smaller satellite galaxies. It is like a sister galaxy to our own, a mirror image of the Milky Way floating in the dark. It gives us a wonderful outside perspective on what our own galaxy might look like if we could travel far away and look back. Our Milky Way and the Andromeda Galaxy are currently moving toward each other. This is not a cause for alarm, as the distances are immense and the process is incredibly slow. They are being drawn together by their mutual gravity in a gentle, cosmic dance. They are expected to merge, but this event is over 4 billion years in the future. When they do eventually meet, it will not be a violent collision, but a slow and graceful merger. The vast distances between individual stars mean that it is very unlikely any stars will actually collide. Instead, the two galaxies will pass through each other, their stars and gas clouds mingling together over hundreds of millions of years. This slow cosmic process will eventually result in the formation of a new, even larger galaxy. The two spiral galaxies will blend and settle into a new shape, likely becoming a giant elliptical galaxy. This is a natural and peaceful part of galactic evolution, a way that galaxies grow and change over cosmic eons. Our galaxy is a living, dynamic place. It is constantly forming new stars. While it is ancient, it is not static. New generations of stars are being born all the time. This star formation happens at a very steady and sustainable rate, estimated to be about 3 to 7 new stars per year across the entire galaxy. These new stars are born in beautiful locations known as stellar nurseries. These are vast, cold, and dense clouds of interstellar gas and dust, primarily hydrogen. These clouds, also called nebulae, are the raw materials from which stars are made. Gravity slowly pulls the gas and dust together into clumps, which grow denser and hotter until a new star ignites at their center. Nebulae are some of the most beautiful objects in our galaxy. These interstellar clouds can be hundreds of light years across. Despite their appearance in photos, they are not solid. They are incredibly diffuse, far less dense than any vacuum we can create on Earth. A piece of nebula the size of our entire planet would have a mass of only a few kilograms. They are like cosmic smoke, visible only because they are illuminated or because they block light. Some nebulae, known as emission nebulae, glow with a distinct reddish color. This beautiful glow comes from hydrogen gas within the cloud. Hot, young stars that have recently formed inside the nebula shine brightly, and their strong ultraviolet light energizes the hydrogen atoms, causing them to glow in the same way a neon sign glows when electricity passes through it. The Orion Nebula is a famous example of one of these glowing star nurseries. Other nebulae are known as reflection nebulae, and they typically shine with a soft blue light. These clouds do not glow on their own. Instead, they are filled with fine dust that is reflecting the light from nearby stars. The dust particles are very good at scattering blue light, while letting red light pass through. This is the same reason our sky on Earth appears blue, and it gives these nebulae a calm, ethereal, and gentle blue hue. Then there are dark nebulae, which are not lit from within or by nearby stars. These are clouds of gas and dust that are so dense they appear as dark, opaque silhouettes against the bright background of more distant stars or glowing nebulae. The famous Horsehead Nebula is a dark nebula, a beautiful shape carved out against a backdrop of glowing red hydrogen gas. There is another type of nebula called a planetary nebula, which has a misleading name as it has nothing to do with planets. These are the beautiful and intricate remnants of stars similar in size to our own sun. When such a star reaches the end of its life, it gently sheds its outer layers of gas into space. The hot, tiny core of the star left behind, called a white dwarf, illuminates these expanding shells of gas, creating spectacular glowing structures that look like cosmic bubbles or rings. The materials made inside stars are the building blocks of everything we know. All the heavy elements in the universe, such as the carbon in our bodies, the oxygen we breathe, and the iron in our blood, were created inside the fiery hearts of stars through nuclear fusion. When these stars end their lives, they release these elements back into the galaxy, enriching the interstellar gas and dust. This star stuff is then recycled, forming new stars, new planets, and eventually new life. Our galaxy is filled with this fine interstellar dust. This is not like the dust in our homes, but is made of tiny microscopic particles of silicates, graphite, and ice. This dust is spread throughout the spiral arms and the galactic plane. Although it is very sparse, over the vast distances of space, it can build up and become opaque, blocking our view of distant stars. This same interstellar dust has a gentle effect on the light that travels through it. As light from distant stars passes through these dusty regions, the dust particles tend to scatter the shorter, blue wavelengths of light more easily, while allowing the longer, red wavelengths of light to pass through more freely. This phenomenon is called reddening, and it causes distant stars to appear redder than they actually are, much in the same way the sun appears red during a sunset, as its light passes through more of Earth's atmosphere. The Milky Way is the dominant galaxy in our local group, but it is accompanied by several smaller companion galaxies. These dwarf galaxies are gravitationally bound to our own and orbit around us. The two most famous are the Large and Small Magellanic Clouds. These are classified as irregular galaxies and are filled with gas, dust, and new stars. They are only visible from the southern hemisphere, where they look like two faint, detached clouds of light. Our Milky Way has grown to its current, massive size by slowly absorbing other, smaller galaxies over its long history. This is a common and gentle process called galactic cannibalism, or merging. When a small dwarf galaxy strays too close, the Milky Way's powerful gravity pulls it apart, and its stars are slowly assimilated into our own galaxy's disk and halo. We can still see evidence of this slow merging process. As these smaller galaxies are pulled apart, their stars are stretched out into long, looping trails that orbit our galaxy. These are known as tidal streams or stellar streams. They are like the ghostly trails or footprints of the galaxies that the Milky Way has merged with in its distant past, a quiet record of its own growth. Our local group of galaxies is itself part of a much, much larger structure. We are on the outskirts of a massive collection of galaxy groups and clusters known as the Virgo supercluster. This supercluster is a flattened structure that contains over 100 galaxy groups and spans over 110 million light-years. Our local group is just one small part of this immense cosmic neighborhood. And even this vast Virgo supercluster is just one lobe of an even grander structure, one of the largest known structures in the universe. In 2014, astronomers defined this as the Laniakea supercluster. This name comes from the Hawaiian language and beautifully translates to immeasurable heaven. Laniakea is a colossal filamentary network of galaxies. It is estimated to contain over 100,000 galaxies, including our own, all moving together through the universe. Our entire supercluster, this immense, immeasurable heaven containing 100,000 galaxies, is not static. The entire structure is moving through space. It is being gently pulled by gravity toward a specific point in the universe. This gravitational focal point is known as the Great Attractor. The Great Attractor is a vast concentration of mass located about 150 to 250 million light-years away. It is not a single object, but a region of space containing a massive collection of galaxy clusters, all pulling together with their combined gravity. It is the gravitational center of our Laniakea supercluster, a downstream point toward which our galaxy and 100,000 others are slowly and calmly flowing. This massive structure, the Great Attractor, is very difficult to observe directly from Earth. This is because it is located in a direction that lies directly behind the plane of our own Milky Way galaxy. The dense gas, dust, and stars of our galaxy's disk create a zone of avoidance, which blocks our view of the distant universe in that direction, hiding this massive structure from our sight in visible light. Galaxies are not all shaped like our own. The astronomer Edwin Hubble was the first to create a classification system for them, and they come in a wonderful variety of forms. Besides spiral and barred spiral galaxies, there are also elliptical and irregular galaxies, each with its own quiet beauty. Elliptical galaxies are smooth, featureless, and shaped like a giant oval or a cosmic football. They can range in size from small dwarf ellipticals to the largest known galaxies in the universe. Unlike spiral galaxies, they have very little gas and dust, and they are not actively forming new stars. They are primarily composed of very old, cooler, red and yellow stars, making them look like giant glowing embers in space. Irregular galaxies are the third main type, and they have no defined or symmetrical shape. Their appearance is often chaotic and disorganized. These galaxies are often shaped by gravitational interactions with their larger neighbors, which pull and stretch them into unique forms. The Magellanic Clouds that orbit our own Milky Way are examples of irregular galaxies. Of all the different types, spiral galaxies like ours are very common, making up about 60% of all the galaxies we have observed in the universe. They are the great stellar pinwheels of the cosmos, defined by their bright star-forming arms and their stable, rotating disks. The color of a galaxy can tell us a lot about its life and its age. Galaxies that appear predominantly blue are typically very active in forming new stars. This blue light comes from the massive, hot, and young blue stars that have recently been born in their spiral arms. These stars burn brightly but live for a relatively short time. Galaxies that appear red or yellow, like elliptical galaxies, are typically much older and have stopped their star-forming processes. Their blue stars have long since faded, and all that remains is the long-lived, cooler, and redder stars. They are the ancient, settled cities of the universe. By this measure, our Milky Way is a blue galaxy. It is still very much alive and active, with vibrant star formation occurring in its beautiful spiral arms. It is a dynamic, evolving, and peaceful home, a place of constant, gentle renewal. The sheer number of galaxies in the universe is a profoundly calming thought. Based on deep field images from space telescopes, astronomers estimate that there are at least 2 trillion galaxies in the observable universe. Each one of these is an island of stars, gas, and dust, separated from the others by vast, quiet stretches of intergalactic space, all floating serenely in the grand, silent expanse. This vast emptiness between galaxies, known as intergalactic space, is the closest thing to a perfect vacuum in the universe. It is not entirely empty, however. This space is filled with a very thin, diffuse gas called the warm-hot intergalactic medium, a tenuous plasma of hydrogen and helium atoms. It is so sparse that there is perhaps only 1 atom per cubic meter. This makes the space between galaxies a place of profound stillness and silence, an enormous, quiet buffer separating the bright, active islands of stars. When we look at galaxies, we are also, in a very real sense, looking back in time. Because light takes time to travel, the light we see from the Andromeda Galaxy left that galaxy 2.5 million years ago. For more distant galaxies, we are seeing them as they were billions of years in the past. This allows astronomers to see the history of the universe simply by looking farther away. The deepest images ever taken, like the Hubble Ultra Deep Field, show us galaxies that were young, forming just a few 100 million years after the Big Bang. These ancient distant galaxies often look smaller and more irregular than modern galaxies, giving us a snapshot of the universe in its infancy. This time travel effect of light means we can never see the universe as it is right now, only as it was in the past. It also means that when we look at a galaxy 100 million light-years away, we are seeing it as it existed when dinosaurs roamed the Earth. This cosmic delay paints a calm, historical picture of the cosmos, where the past is always visible. The light we see from galaxies is not just visible light. Galaxies shine across the entire electromagnetic spectrum. In radio waves, we can see the cold, slow-moving hydrogen gas, the raw fuel for future star formation, spread far and wide throughout a galaxy's disk. In infrared light, we can see through the opaque veils of dust and observe the warm, gentle glow of newly forming stars that are hidden deep inside their dusty cocoons. X-rays, on the other hand, reveal the very hot, energetic processes. But in a quiet galaxy like ours, this activity is minimal confined to specific objects rather than the whole galaxy. Studying these different types of light gives us a complete and peaceful picture of a galaxy's full life cycle. The rotation of spiral galaxies is a wonder of stability. The stars, gas, and dust all orbit the galactic center, but they do not orbit as a solid object, like a wheel. Instead, they follow a differential rotation, where stars closer to the center might complete an orbit faster than stars farther out. However, one of the most profound discoveries about galaxies is that this is not entirely true for the outer regions. Stars in the outer parts of spiral galaxies are moving much faster than they should be, based on the amount of visible matter. This observation is the strongest evidence for the existence of the invisible dark matter halo, whose gentle, unseen gravity provides the extra pull needed to keep these fast-moving outer stars from flying off into intergalactic space. This dark matter halo is a vast spherical cushion of mass that surrounds the entire visible galaxy, extending far beyond the brightest spiral arms. It is a stable, invisible scaffolding that dictates the galaxy's structure and its calm, steady rotation. The gas and dust between the stars, the interstellar medium, is the lifeblood of a galaxy. While it looks like dark, empty patches in photographs, this medium is where all the action of renewal takes place. It is this medium that slowly, over millions of years, condenses to form new stars. And it is this medium that is enriched by the elements created in previous generations of stars. This creates a continuous, gentle cycle of cosmic recycling. Stars are born from the gas. They live their lives by fusing light elements into heavier ones, and when they end their lives, they return these new, heavier elements back into the gas. This ensures that each new generation of stars and planets is built from material that is slightly more complex than the last. The vast structures of the universe are built from galaxies. Galaxies themselves are not spread randomly throughout space. They are organized into a vast, beautiful web-like structure known as the cosmic web. On the largest scales, the universe resembles a three-dimensional network with long, delicate filaments of galaxies and dark matter stretching across billions of light years. Where these filaments intersect, they form dense, rich clusters of galaxies. In between these filaments are enormous, mostly empty regions known as cosmic voids. Our own Milky Way is located within one of these long cosmic filaments, a resident of the Laniakea supercluster, all drifting peacefully in this grand, interconnected pattern. The scale of these voids is just as impressive as the galaxies themselves. These are vast, quiet expanses, hundreds of millions of light years across, where there are very few, if any, galaxies. They are the great silent deserts of the cosmos, places of extreme emptiness and stillness. The existence of these voids is a natural consequence of gravity, pulling matter together into the filaments and clusters, leaving these vast regions of calm behind. The spiral arms of a galaxy, which look so solid and permanent, are not fixed structures. They are not like the spokes of a wheel, with the same stars always in them. Instead, they are density waves. Think of them as a slow-moving cosmic traffic jam. The wave itself, the spiral arm, is a region of higher gravity and density that moves through the galactic disk more slowly than the stars and gas do. As stars and gas clouds orbit the galaxy, they catch up to this slow-moving density wave. When they enter the arm, the higher gravity squeezes the gas clouds, triggering a burst of new star formation. This is why the spiral arms are so bright. They are lit up by the hot, young, blue stars that were just born there. The stars themselves, including our sun, are not permanently stuck in these arms. They pass through them, shine brightly for a time, and then continue on their orbit, moving out of the arm and into the clearer, less dense region between the arms. Our sun is currently passing through the Orion Spur, this smaller, quieter arm. This means we are constantly and very slowly moving through the galaxy's beautiful wave-like pattern. This process is slow, stable, and has been happening in our galaxy for billions of years. a continuous, gentle engine of stellar creation. Many galaxies, including our own, have a beautiful, faint, and enormous spherical component called the stellar halo. This is different from the dark matter halo. The stellar halo is a sparse, puffy cloud of very old stars and ancient star clusters that surrounds the entire main disk of the galaxy. These are some of the first stars that ever formed in the Milky Way, more than 12 or 13 billion years ago. They do not orbit the galaxy in a neat, flat circle as our Sun does. Instead, they travel on long, looping, and eccentric orbits that take them far above and below the galactic plane, plunging through the disk and back out again. These ancient stars are like a quiet, ghostly cloud of witnesses to our galaxy's entire history, remnants from its very birth, still held gently by its gravity. Within this stellar halo, you can find the globular clusters. These are magnificent, dense, and perfectly spherical collections of stars. A single globular cluster can contain hundreds of thousands, or even a million, very old stars, all packed tightly into a ball only a few dozen light years across. Our Milky Way has about 150 of these ancient clusters, and they orbit the galaxy as satellites. They are like self-contained miniature galaxies, ancient relics from the dawn of time, surviving intact and moving with a slow, predictable grace through the vast, quiet halo of our galaxy. The globular clusters that drift through the galactic halo are some of the most ancient objects in our galaxy, like self-contained museums of the early universe. The stars within them are all of a similar age, having formed together in a single burst more than 10 to 12 billion years ago. This makes them significantly older than our own Sun. Because they are so old, these stars are also chemically different from our Sun. They are metal poor, meaning they contain very few elements heavier than hydrogen and helium. This is because they were formed from the original, pristine gas that existed in the universe before many generations of stars had a chance to create and spread heavier elements. They are a direct window into the chemical conditions of our galaxy's infancy. Their orbits are also fundamentally different from the stars in the disk, like our Sun. They do not participate in the calm, flat rotation of the galactic plane. Instead, they travel on highly elliptical, plunging orbits that are randomly oriented, swooping high above the galaxy, diving through the dense central bulge, and swinging far out into the halo again. These chaotic but stable orbits are a relic of the time when the Milky Way itself was first collapsing and forming. Inside these globular clusters, the density of stars is astonishing. In the core of a cluster like Omega Centauri, stars are packed thousands of times more densely than in our own solar neighborhood. From the perspective of a hypothetical planet in such a cluster, the night sky would be a spectacular, blazing tapestry, filled with thousands of bright nearby stars, a sky without true darkness. In contrast to these ancient, dense globular clusters, our galaxy's disk is also home to a much younger type of star cluster, known as an open cluster. These are the younger siblings of globular clusters. Open clusters, like the Pleiades or the Hyades, are also groups of stars that were born together from the same giant molecular cloud. However, they are much smaller, containing just a few hundred to a few thousand stars, and they are much, much younger, typically only a few 100 million years old. Unlike globular clusters, open clusters are found only within the flat plane of the galaxy, in the spiral arms where star formation is active. They are also only loosely bound by gravity. As they orbit the galactic center, they are gently pulled apart by the gravitational tides of the galaxy and by encounters with other gas clouds. Over a few 100 million years, their member stars will slowly drift apart and disperse, mingling with the other stars of the galactic disk. Our Sun was almost certainly born in an open cluster just like this, but its sibling stars have long since scattered across the galaxy. Our galaxy is permeated by a vast and complex magnetic field. This field is incredibly weak, about 1,000,000 times weaker than the magnetic field at the Earth's surface, but it spans the entire galaxy. It is woven through the spiral arms, the halo, and the central bar. This galactic magnetic field is generated by the collective motion of charged particles and plasma moving within the galaxy, a process similar to the dynamo that creates Earth's magnetic field. This faint but enormous field is strong enough to influence the paths of charged particles, known as cosmic rays, guiding them as they speed through the galaxy. It also helps to shape the interstellar gas clouds, guiding the flow of matter and influencing where and how new stars are formed. The galaxy is filled with these cosmic rays, which are high-energy particles, mostly protons and atomic nuclei, that travel through space at nearly the speed of light. They are not a form of light, but are actual particles of matter that have been accelerated to incredible energies. Most of the cosmic rays we detect from within our galaxy are thought to be produced in the shock waves of supernovae, the explosive endings of massive stars. As they travel, they are deflected and corralled by the galaxy's magnetic field, causing them to fizzle and change direction constantly, making their exact origin point very difficult to trace. This field acts as a magnetic shield, trapping many of these particles within the galactic halo. The space between the stars is not just filled with gas and dust, but also with a surprising variety of complex molecules. Using radio telescopes, astronomers have identified over 200 different types of molecules floating in the vast, cold molecular clouds. These range from simple molecules like water and carbon monoxide to much larger organic molecules. Among these are polycyclic aromatic hydrocarbons, or PAHs, which are carbon-based molecules also found on Earth in soot and grilled foods. These large molecules are thought to be very common in space and are responsible for some of the complex infrared light we see from nebulae. In fact, when astronauts in orbit describe the smell of space after a spacewalk, the sharp, metallic, or burnt steak scent they report is thought to come from these very same hydrocarbon compounds clinging to their suits. Our galaxy breathes in a continuous slow-motion cycle. This process is sometimes called the galactic fountain. Hot gas, heated by supernova explosions and the powerful stellar winds from young massive stars, is blown outwards from the galactic disk. This hot gas expands and rises, creating a massive diffuse atmosphere or corona of gas around the galaxy. This hot gas can travel for thousands of light years, high up into the galactic halo. Over millions of years, this gas will cool down. As it cools, it condenses and begins to fall back down toward the galactic plane, like a gentle, galaxy-wide rain. This returning gas, now enriched with new elements from the stars that expelled it, provides fresh fuel for the next generation of star formation. This creates a vast, sustainable ecosystem, constantly recycling its own material. The disk of our galaxy, where we live, is not a perfectly still plane. Our sun, along with all the other stars in the disk, has its own gentle, vertical motion. As the sun orbits the galactic center, it also bobs up and down, oscillating through the galactic plane. This motion is like a horse on a carousel, moving up and down as it goes around. Our sun passes through the central, densest part of the galactic plane approximately once every 30 million years. We are currently moving upward, having passed through the plane about 3 million years ago. This gentle, wave-like motion is a normal part of orbiting within a disk, influenced by the collective gravity of all the stars and gas in the galactic plane. The spiral arms of our galaxy, the bright star-forming regions, are not all identical. Galaxies like ours are often classified by the appearance of their arms. Some galaxies have very clearly defined, long and continuous arms, which are known as grand design spirals. Others, however, have arms that are more patchy, fragmented, and less distinct. These are called flocculent spirals, meaning fleecy or fluffy looking. The Milky Way is thought to be somewhere in between, but it does possess several major grand design arms. This difference is thought to be related to the galaxy's environment and internal structure. Grand design spirals are often triggered by a gravitational disturbance, such as a close pass by a companion galaxy, which organizes the density wave into a clear, strong pattern. Our closest large neighbor, the Andromeda Galaxy, has a companion galaxy, M32, which may be responsible for its own grand design structure. Andromeda is also a much larger galaxy than the Milky Way in terms of its total extent. While its visible disk of stars is only moderately larger than ours, its vast halo of stars and dark matter extends much, much farther. Its stellar halo is over 1 million light-years across, meaning it is already touching the outer halo of our own Milky Way galaxy. The two galaxies are already beginning to mingle their most distant outlying stars. Andromeda is also home to the largest known globular cluster in our entire local group. This cluster, named Mile 2 or G1, is incredibly massive, containing the equivalent of over 10 million suns. It is so large that some astronomers believe it is not a true globular cluster at all, but is actually the leftover, stripped-down core of a small dwarf galaxy that Andromeda consumed in its past. This provides more evidence that galaxies grow by merging with smaller companions. Our local group of galaxies contains a third large member, though it is smaller than both the Milky Way and Andromeda. This is the Triangulum Galaxy, also known as M33. It is also a spiral galaxy, but unlike the Milky Way, it is not a barred spiral. It is a beautiful, classic spiral with fluffy, flocculent arms that are brimming with star formation. It is located about 3 million light-years away and is the third largest galaxy in our local group. The Triangulum Galaxy is famous for its enormous, bright pink regions of star formation. One of these, known as NGC 604, is one of the largest stellar nurseries in the entire local group. It is a vast cloud of glowing hydrogen gas, more than 1,500 light-years across, and it contains hundreds of newly formed massive blue stars. It is a stunning example of the active creative processes happening in our galactic neighborhood. The Triangulum Galaxy may actually be a distant companion to the Andromeda Galaxy. Its motion through space suggests it is gravitationally bound to Andromeda, orbiting it in a long, slow dance. The two galaxies may have had a close encounter in the past, which could be responsible for triggering the intense star formation we now see in Triangulum's arms. The rest of our local group is made up of over 50 smaller dwarf galaxies. These come in two main types: dwarf irregulars, like the Magellanic Clouds, which are still actively forming stars, and dwarf spheroidals, which are much fainter, more diffuse, and are composed almost entirely of very old stars. These dwarf spheroidals are like the ghostly, faded remnants of galaxies, having used up all their gas long ago. They are incredibly faint and difficult to see, and astronomers are still discovering new ones orbiting our own Milky Way. The faintest of these ultra-faint dwarf galaxies are the most dark matter-dominated objects we know of. Their visible stars are so few and far between that their mass is almost entirely composed of dark matter. The gravity of this dark matter is the only thing holding these faint, ancient star systems together. Sometimes, when two galaxies pass very close to each other, their mutual gravity can pull out long, thin streamers of stars and gas. These are known as tidal tails. These beautiful arcing structures can stretch for hundreds of thousands of light years, tracing the path of the galactic encounter. They are a visible record of the gravitational dance between galaxies, a quiet and graceful reshaping of their forms. In rare cases, a galactic encounter can create a very specific and beautiful structure, a ring galaxy. This happens when a smaller galaxy passes directly through the center of a larger disc-shaped galaxy. The collision is not a crash, but a gravitational ripple. The smaller galaxy punches through the disk, and its gravity creates an expanding circular wave of density, much like the ripple created by dropping a stone into a pond. This wave sweeps outwards, compressing gas and dust as it goes, triggering a massive, ring-shaped burst of new star formation. The Cartwheel Galaxy is the most famous example of this, a stunning cosmic wheel with a bright blue outer ring of new stars and a smaller inner core, Between the active star-forming spiral galaxies and the old, quiet, elliptical galaxies, there is an intermediate class of galaxy known as a lenticular galaxy. The word lenticular means lens-shaped. These galaxies have a bright central bulge and a flat, rotating disk, just like a spiral galaxy. However, they have used up or lost almost all of their interstellar gas and dust, so they have no spiral arms and are no longer forming new stars. They are retired spiral galaxies, composed mostly of older yellow and red stars. They are a snapshot of what our own Milky Way might look like many billions of years in the future, after its gas has been exhausted. Some galaxies have centers that are incredibly bright, shining with more light than all the billions of stars in the rest of the galaxy combined. These are known as active galactic nuclei, or AGN. This intense light is not from stars. It is generated by the supermassive black hole at the galaxy's center, which is actively feeding on a large swirling disk of gas and dust that is falling into it. As this material spirals inward, it is heated to extreme temperatures by friction, causing it to shine with ferocious brightness. The most luminous of these active centers are called quasars, and they are some of the most distant and brightest objects we can see in the entire universe. While they are very energetic, they are also a normal phase in the life of many young galaxies. Our own Milky Way is not an active galaxy. Its central black hole is quiet, with very little material falling into it. The color of a galaxy is a beautiful indicator of its history. Blue galaxies are places of new birth, with their color dominated by hot, young, massive stars. Red galaxies are places of ancient calm, their color coming from old, cool, long-lived stars. This leads to a clear color magnitude diagram for galaxies, where galaxies tend to be either red and dead, old ellipticals, or blue and active, young spirals. There are very few galaxies in the middle, in a green valley, which suggests that when a spiral galaxy's star formation shuts down, its transition to a red galaxy is a very rapid one, cosmically speaking. If you could somehow gather all the light from all the galaxies in the universe and average it all together, what color would you get? Astronomers at Johns Hopkins University did exactly this. They analyzed the light from over 200,000 galaxies and combined their spectra. The resulting average color of the universe is a very pale, gentle beige white. They gave this color an official name, cosmic latte. This color represents the combined light of all the ancient red stars and all the young blue stars, blended together into a single soft hue. Gravity's effect on light itself creates one of the most beautiful and subtle phenomena in the cosmos: gravitational lensing. Albert Einstein's theory of general relativity predicted that massive objects would warp the fabric of space-time, and that light would have to follow this curve. When light from a very distant galaxy passes by a much closer massive galaxy or cluster of galaxies, the gravity of the foreground object acts like a giant, imperfect lens. It bends and magnifies the light of the distant galaxy. This can distort the distant galaxy's image, stretching it into long, thin arcs, or even creating multiple separate images of the same galaxy. This strong lensing effect is not only beautiful, but it allows astronomers to see galaxies that are so distant they would otherwise be too faint to detect. There is also a weak lensing effect, where the gravity of cosmic structures subtly stretches the shapes of background galaxies over the entire sky. By mapping this faint statistical distortion across millions of galaxies, astronomers can create a map of the invisible dark matter that is causing the lensing. This is one of the primary ways we see the invisible dark matter and map out the vast, unseen framework of the cosmic web. The Magellanic Clouds, our two small companion galaxies, are not on a perfectly clean orbit. As they travel, they are leaving behind a massive trailing stream of neutral hydrogen gas, which has been pulled from them by the gravity of the Milky Way. This is known as the Magellanic Stream. It is an enormous, arcing river of gas that wraps more than halfway around our galaxy, a visible trail of the cloud's long journey. This gas is slowly falling into the Milky Way's halo, providing a new source of fuel that will eventually make its way to the disk and help create new stars. This is another form of galactic recycling, where our large galaxy slowly sips gas from its smaller companions. Not all the gas in our galaxy's halo is from these streams. Astronomers have also detected high-velocity clouds, which are mysterious clouds of gas moving at very high speeds, plunging toward the galactic disk. Their origins are not fully understood. Some are likely the remnants of the Magellanic Stream or other tidal debris, while others may be the pristine, leftover gas from the formation of the local group falling into the Milky Way for the very first time. These clouds are like a gentle cosmic rain, delivering fresh, primitive material to our galaxy. Our solar system exists within a special region of the galaxy known as the Galactic Habitable Zone. This is a Goldilocks region, an annulus-shaped ring within the galactic disk that is considered the most likely place for complex life to develop. It is a region that is just right in several ways. It is far enough from the galactic center to be safe from the intense radiation and the disruptive gravity of the dense central stars. It is also close enough to the center to contain a sufficient concentration of metals, the heavier elements needed to form rocky planets like Earth. If we were too far out in the galaxy's edge, there would not have been enough heavy elements to build our world. Our position in the Orion Spur is a calm and stable place within this habitable zone. We are also lucky in our timing. Our Sun is a population 1 star, meaning it is a relatively recent star, rich in metals. The very first stars in the universe, population 3 stars, were made of only hydrogen and helium and could not have supported life as we know it. We live in a generation of the universe where the raw materials for life are abundant, all thanks to the continuous cycle of stellar birth and death that has enriched the galaxy over billions of years. The galaxy is mostly empty space. Even in the dense-looking spiral arms, the distance between stars is immense. If our Sun were the size of a grapefruit, our nearest neighbor star, Proxima Centauri, would be another grapefruit over 2,000 miles, or 3,200 kilometers, away. This vast, empty stillness is why galaxy mergers are so peaceful. The galaxies, which are collections of these widely separated points of light, simply pass through each other like two clouds of smoke, their individual stars rarely, if ever, colliding. Their gas clouds, however, do collide, triggering new star formation, but the stars themselves slide past one another in a slow gravitational waltz. The galaxy is also transparent to certain types of particles. Neutrinos are fundamental particles that are created in the nuclear fusion reactions inside stars. They have almost no mass and no electric charge, so they do not interact with matter. Trillions of neutrinos from our Sun pass through your body every second, and through the entire Earth without stopping. Neutrinos from distant supernovae and from the core of our own galaxy travel in perfectly straight lines, passing through gas, dust, and stars as if they were not there, carrying information directly from the hearts of these cosmic engines. The light from our galaxy, as beautiful as it is not eternal. The process of star formation is finite. It relies on a limited supply of cool interstellar gas. Over vast timescales, our galaxy's gas reserves will be used up. The rate of new star formation, which is already very steady, will begin to slow down. Billions of years from now, after the merger with Andromeda, the resulting new galaxy will have used up most of its available gas. New star birth will become rarer and rarer, until it eventually ceases almost entirely. The galaxy will slowly fade from its active blue phase into a quiet red phase. The last stars to be born will be the small, cool, dim red dwarfs. These stars are incredibly long-lived. They sip their hydrogen fuel so slowly that they can shine for trillions of years, far, far longer than the current age of the universe. They will be the last lights of the galaxy. After all the larger stars have burned out, these red dwarfs will be the only stars left. Tiny, faint embers glowing in the dark, preserving the last vestiges of light in an ancient, quiet, and peaceful universe. The stars themselves will eventually fade, leaving behind cold, dark remnants like white dwarfs, neutron stars, and black holes. The galaxy, now a vast collection of dark, silent objects, will continue its steady, unseen rotation, held together by gravity. Even then, on timescales so vast they are almost impossible to imagine, the galaxy itself may dissolve. The orbits of these dark remnants will slowly be disrupted, and they may be ejected one by one, drifting alone into the cold, empty intergalactic darkness. The universe will become a place of profound, unending stillness, a final, peaceful quiet after a long and beautiful cosmic day. This final state of the universe, with our faded, isolated galaxy, is known as the heat death, but a more peaceful way to imagine it is as the Great Stillness. It is not a violent end, but a slow, gradual, and ultimate settling of all things into a state of perfect, uniform equilibrium and profound quiet. Before this distant final end, our galaxy will have billions of more years of active, vibrant life. Its stability is truly remarkable. Our sun, for example, is on an extremely stable and predictable orbit. It is in what is known as a corotation resonance. This means that our sun is moving at almost the same speed as the galaxy's spiral arms themselves. Because we are keeping pace with the density wave, we are not constantly passing in and out of these dense, chaotic, and high-activity regions. We stay within our quiet Orion spur for long periods, avoiding the frequent disruptive gravitational pulls and the intense radiation from supernova explosions that are more common inside the major arms. This orbital stability is a key factor in the long-term, peaceful evolution of our solar system, a calm harbor in the galactic stream. The very concept of empty space in our galaxy is itself misleading. The interstellar medium, while incredibly tenuous, is a dynamic and complex place. It is sculpted by what is known as galactic weather. This weather is not stormy in a terrestrial sense, but is a slow-motion process of interacting forces. Supernova explosions and the powerful winds from clusters of young, massive stars inflate vast, expanding superbubbles of hot, thin gas. These bubbles can be hundreds of light years across. As they expand, they sweep up and compress the surrounding cold gas, acting as a snowplow that triggers the next wave of star formation along their outer edges. It is a self-regulating, creative cycle where the end of one generation of stars gently seeds the birth of the next. Our galaxy is also filled with a vast, invisible ocean of subatomic particles. Trillions of neutrinos, born in the nuclear furnaces of the sun and other stars, pass through our planet and our bodies every single second, completely harmlessly. They are ghost particles, interacting so weakly with matter that they can travel from the core of a star or from a distant galaxy in a perfectly straight line, passing through planets, dust clouds, and entire galaxies as if they were nothing but empty space. They are the universe's most peaceful messengers, carrying information from the very heart of stellar engines. The great silence of the cosmos, the fact that we do not hear signals from other civilizations, is perhaps the most calming fact of all. The galaxy is 100,000 light-years across, and it has existed for over 13 billion years. The sheer scales of space and time are beyond our comprehension. This silence is not a sign of emptiness or danger, but a testament to the profound, insulating vastness of the cosmos. It grants every world a form of ultimate privacy and peace. It suggests that life, if it exists elsewhere, is like our own, a small, precious, and quiet phenomenon sheltered by the immense, protective buffers of empty space. The light we see from stars and nebulae is only a tiny fraction of the information the galaxy sends us. When astronomers create the beautiful, colorful pictures of galaxies, they are often translating light our eyes cannot see. They assign visible colors like red, green, and blue to different invisible wavelengths, such as infrared, ultraviolet, or even X-rays. Infrared light, for example, allows us to see the gentle, warm glow of dust and forming stars that are hidden deep inside opaque clouds. This false color imaging is not a deception. It is a form of translation, allowing us to see the full, complex, and layered beauty of the galaxy's invisible processes. The planets we have discovered in our galaxy are a testament to its creative potential. In just the last few decades, we have confirmed the existence of thousands of exoplanets orbiting other stars. The data from these discoveries suggests that, on average, there is at least one planet for every star in the Milky Way. This means our galaxy is home to a minimum of 100 to 400 billion planets. Many of these are gas giants like Jupiter, but many others are smaller, rocky worlds. The sheer number of them suggests that the galaxy is filled with countless quiet, stable systems, worlds of every conceivable kind, all held in gentle, predictable orbits around their parent stars. Among these are the rogue planets, which are perhaps the most serene objects in the galaxy. These are worlds that have been ejected from their original solar systems and now drift unbound, untethered to any star. They move silently through the vast, cold darkness between the stars. While their surfaces would be frozen, it is possible that larger worlds could maintain warm, liquid oceans beneath a thick, insulating shell of ice, warmed by the slow decay of radioactive elements in their core. They are complete, self-contained worlds, traveling in a state of perpetual, peaceful isolation, their journeys lasting for eons. The concept of the Laniakea supercluster, our immeasurable heaven, is one of flow, not structure. It is not a thing that is held together by gravity, but rather a watershed region. The great attractor is the valley, or the central gravitational basin of this watershed, and our galaxy is simply following the contours of space-time, flowing gently downhill toward it, like a drop of water in a vast, slow-moving cosmic river. But this flow itself is being opposed by the accelerating expansion of the universe, driven by dark energy. This expansion is a gentle, uniform force that is slowly stretching the fabric of space-time itself. This means that while our local group will stay together, the Laniakea supercluster is a temporary gathering. The distant galaxies and clusters within it are being pulled away from us by this expansion, faster than gravity can hold us together. This is not a violent process, but a slow, quiet dissolution. Over countless billions of years, this expansion will carry all other superclusters away from our own, until they have moved so far that their light can no longer reach us. Our local group will be left as a single, massive, isolated galaxy, alone in an observable universe that has become, for all intents and purposes, completely empty, leaving us in a final, quiet, and stable cosmic solitude.